Okay, let's go ahead and get started. My name is Becky Dipple, and I will be your moderator and producer for today's IWCS webinar series. And in a few minutes, my colleague Dave Cadu, IWCS CEO and Director, will be coming online and joining us. Dave Cadu was planned to be your moderator this morning, but he just had a power outage, so he's getting set up right now, and he'll be with us shortly. But while we wait, we have a few housekeeping items before we get started. Please note that as an attendee, you are part of a large audience. During the presentation, all participants will remain in listen-only mode. As a reminder, this event is being recorded for rebroadcast. We encourage you to submit written questions at any time during the presentation using the chat panel on the right of your screen. After typing your questions in the space at the bottom, hit the send button. Your questions will be addressed, time permitting, at the end of the presentation. Our webinar series event is hosted by the IWCS Cable and Connectivity Industry Forum. IWCS offers a series of webinars on important trends and technologies from the perspectives of our supply chain technology leaders and sponsors of our IWCS Cable and Connectivity Industry Forum. Today we welcome Dr. Alan McCurdy, Distinguished Member of Technical Staff at Lightera in Georgia, USA. Alan will be presenting his paper on core identification and geometry specifications in multicore optical fibers. Alan McCurdy is currently a distinguished member of technical staff at Lightera. He works on noise and fiber measurement problems in optical fiber communications. Alan has worked in telecommunications since joining the Enterprise Networks Group at Lucent Technologies in 1998. Prior to that, he spent 9 years on the electrical engineering faculty of the University of Southern California, working in high-power microwave research. He earned BS degrees in chemical engineering and physics from Carnegie Mellon University and master's and Ph.D. degrees from Yale University. He is a member of IEEE and Optica. We welcome Alan to present his technical paper at today's IWCS webinar series event.
Thank you, Becky. I'm trying to get into share mode right. There we go. Does that look okay?
That looks great, Alan. Thank you. Take it away.
Okay. Well, thanks for that introduction. And thank you all for joining. We'll be talking about multi-core fibers today, and particularly some of the geometrical issues on how to specify where the cores are. So we take different multi-core fibers and try to connect them together. We get minimal loss. Briefly, we'll talk a bit about core identification as well. This was a paper that Roman Shabatkin, my co-author, gave at the IWCS meeting last fall. Tom Liang and Tristan Kremp also contributed to this work. So without further ado, we'll talk about core identification, tolerancing MCF geometry, which basically means putting tolerances on where the cores actually will be. There's two methods we're going to describe here. One is sort of an intuitive method, which has historically been relevant, that is just specifying the pitch between the cores and the radial position of the cores. We're going to then talk about a little more complicated method where we rotate the cores against a design template, and that seems to be the preferred approach if you were to choose one over the other. And then we'll do some practical employment of these geometry tolerances, and we'll look at 2-core case and a 4-core case. And then there'll be a little bit of experimental data at the end where we validate this business of fusion splicing multi-core fibers together with imperfect geometries, and what sort of splice losses do we end up with, and how well is that predicted? And then we'll conclude. Okay, so with multi-core fiber, of course, now we have many cores inside a cladding structure. Generally, these cores are basically identical optically, usually they are, and it may be very hard to distinguish one from another. So in the case of a 2-core fiber, let me see if I can get a pointer going here. There we go. Case of a two-core fiber, we have a couple of planes of symmetry here, but the important one is this blue one. Core 1 and core 2 will map into each other, and if they're identical cores, we can't tell them apart. So sometimes one would add a third object, a third core, as it were, which perhaps is very small and doesn't guide light, hopefully doesn't disturb the propagation properties of any of the other cores. We call this thing a marker, and if we locate it, perhaps, let's say, near core 1, then we can distinguish the cores apart, and we look at the fiber from either end, and we can tell which is core 1 and which is core 2. Other approaches to this have been using non-uniform cores, different refractive index profiles, for example, in core 1 and core 2, so that given the imaging techniques that you have for looking at geometry or fusion splicing or looking at connectors, you can tell one from the other. You could offset the cores so they're not symmetrically spaced around the cladding center, and this has been done in practice in some recent submarine work. For example, core 1 might be the core that's closest to the cladding edge. With more cores, things get obviously more complicated. And here's some case of all the planes of symmetry with a symmetric four-core structure. Here you could imagine putting a symmetric marker in that would allow you to distinguish the top two cores from the bottom two, but you couldn't tell core 1 from 2 or 3 from 4. Or you could do an asymmetric marker, such as shown here, where now you can actually, you break all the planes of symmetry, and you can now say, for example, with an appropriate rule, the marker is closest to core 1. Therefore, we know that would be core 1. And in the direction that we go from the marker to core 1, that would be the direction we would go as we count up on the consecutive cores. So if core 1 is closest, as we go from the marker to the core 1, core 2 would be the next one around, core 3 and 4, and we would have sort of a clockwise numbering pattern that's used here. So this one is quite popular, and this one has been used a bit on 2 cores. Not clear how this maps into a 4-core structure, might be more complicated, but that's what we have. Okay, so there have been a number of papers published arguing how much identification you really need on these cores. Are there some simpler ways to go? And if you only need to identify transmitter and receiver cores, this kind of method actually is not bad. But historically, fiber manufacturers have delivered a lot of optical data with every core that they ship. And so with single core fiber, generally, all the dispersion properties, the attenuation properties, for example, of the core. And if you have 2 cores, probably you would like to know all that information on each of those cores individually. So it's not clear customers are going to accept the idea of getting cores that, for example, just correspond to some ITU recommendation and without specific numbers to back that up. So a problem with these asymmetric markers is the idea of polarity. That is that if we look at what's going on at the 2 ends of a multi-core fiber, there's something different happening. Again, if we employ the rule that the marker is closest to core number 1 and the cores get numbered in the direction that we go when we go from the marker to core 1, you would see that these cores would be numbered in a counterclockwise fashion. And at the other end of the fiber, the cores would be numbered in a clockwise fashion. That's awkward because then if you take 2 multi-cores and you want to attach them to each other, if you don't attach the right ends, you'll get cores mixed up. And so in this case, 2 counterclockwise cores are trying to connect to each other, and it's not working so well because cores 1 and 3 are fine, but 2 and 4 get flipped. So polarity is sort of a bane of the multi-core environment ecosystem right now, and people are trying to find ways around it. But certainly if you have to track the ends of every fiber as you go through manufacture and deployment, as you go through the cabling process, et cetera, that could lead to problems. There are a number of standards groups and companies and MSAs and what right now getting established to deal with these things and work out the ways of tracking polarity and the necessity for doing so through different deployment options. And so that's ongoing work, and it'll take a while. So again, back to the geometry idea. If we start with a single core geometry, what have we done? Well, really the one metric on single core geometry is how well the core center is placed inside the cladding, how close it is to the cladding center. And in standards fibers, we have, for example, ITU specified fibers, we have 0.6 micron offset that's allowed. And so anywhere in this violet region is legal for the core to be positioned. And ideally, you'll be as close to the center as possible. And the reason why you constrain this is if you were to attach two of these single core fibers together, if there's too much offset here, you're going to get a lot of connection loss. And if you can keep it below 0.6 microns, then the connection loss stays relatively low. With multi-core fiber, the problem now is we have a lot of cores that are off the fiber center or the cladding center. The symmetry is blown, and we still do have a reference we could use as the cladding center. But then the question is, what will we use for the azimuthal reference? You can't identify a simple set of XY coordinates that are unique, nothing special there. And so historically, one thing that's been done, and this is in the sense of not a production or customer-based environment, but more or less R&D, is that one specifies the pitch and the radius. For example, the radius of each core center from the center of the fiber. So this radius right here would be one way to get a radial element to the core position. And then if you measure the pitch between the cores, the distance between the cores, that gives you something like an angular coordinate. And so the pitch radius method has been used at some level at this point. So you can add tolerances, half a micron or something to each the radius and the pitch. And we'll see there are some issues with doing this. And a potentially better way of doing it is actually taking your fiber in question and aligning it against a master template, which contains the design core positions. You would then rotate your fiber to minimize the differences between your fiber core positions and the design positions. And then you could assign some sort of error to that. Now, again, this is not a new idea. This has been done for some time, particularly in fusion splicers. The algorithms that they use for multi-core fiber are based exactly on this kind of idea. So again, to review here, the pitch radius method is this. You're talking about the offset of the cores from the cladding center. That's the radius part of it. The pitch gives you the distance between the cores. And for simple structures like this symmetric four core, it's not too bad. However, for tolerancing, to say that, you know, exactly how accurately do the cores have to be in compliance with this pitch and this radius, we'll see there are some issues with tolerancing. To run through the rotate to template method, I'm going to use this following slide. We'll focus on just one core in the pattern. And so here's the core in the real fiber we're trying to qualify. Here's where that core is supposed to be in the dashed or red circle. And there, of course, could be many cores in this pattern. This is only one. We could imagine rotating the entire pattern by some angle alpha and try to get all the cores closer to where they're supposed to be. They could be off both an angle, and they could also have different radial positions. So there's several things to worry about here. The distance between the core and its desired position can be given by this expression, with alpha being the sort of the variable here. We could define the error in this fiber as the sum over all these distances for every single core. We could add them all up and create some cost function, and we could then optimize with respect to alpha. We could optimize this cost function with respect to alpha here. And in the case I've shown here, you can actually analytically derive the answer. It's pretty simple. And it involves a ratio of a bunch of these things with just the angular difference between where the cores are and where they're supposed to be. And then there's some scaling here by the radial distances of the core compared to where it should be. And then, for example, you could report the worst case offset, and then that would sort of be then the error. That would be the thing you would specify. You have to be within so many tenths of a micron, and their worst case core would establish that. One way to do it. So the idea of summing the square distances, that's one way to create a cost function. It may not be the best way. And so this is actually something that's still being considered, IEC standards in particular. What sort of cost function should you use? If we imagine a core template or design template that looks like this for 4 cores, And it turns out maybe the cores are actually in these green circles. I chose a particularly awkward case here. That's where core 1, 2, and 3 are off slightly off in a clockwise direction, and core 4 is badly off in a counterclockwise direction. So when we optimize, and I assigned some angles here, just they're not to scale, of course, but that's the idea. When we optimize according to this thing, what we're going to find is that we're going to do the optimization will say, well, we have 3 bad cores here. Let's actually rotate counterclockwise and make them a little better. And at the expense of this guy who's already too far in the counterclockwise direction. So when we actually look at the angles after this optimization, we find, yes, indeed, 3 cores got better, but 1 got worse. And this may be unacceptable because we may be now beyond some limit for splice loss or something, which tends to scale as some power of the distance offset between the cores. So instead, we could think of going, create a new cost function which includes the 4th powers of the distance to more heavily emphasize the bad cores that are way off. So for example, this core would now have more weight. And when you do this kind of optimization, you find, well, in fact, a small clockwise rotation is recommended, which then slightly decreases the error on core 4 and then increases the error slightly on all the other ones. Still something to be decided among standards, and it may eventually be left to manufacturers to figure this out. One other thing that's come up recently in standards is the idea of fixing radial errors. This whole rotation idea that I'm talking about just gets the angular alignment as best as possible. But we know with single core fibers, you can, on most splicers, do core alignment as well. So you're not just aligning the cladding, instead you're focusing on what's really important, and that's getting the 2 cores aligned. If one of the cores is slightly off center, your splice machine can offset this in a certain fashion and then fuse it and then get those cores to kind of pull into some kind of linear array here, linear line. And you see there's something strange happening at the junction, but as you get away from the splice point, actually the cores are aligned pretty well. And in fact, it's well known that you improve splice loss by doing this. So can you do this with multicore fiber? Can you core align? Certainly you could calculate centroids of different core patterns and consider an offset of that centroid from a design centroid. So you could think about doing some radial movement. Has not been demonstrated that I know of, but we could actually simulate this pretty easily and figure out what benefits it would have. Okay, I'm going to run through a couple of pitfalls with the pitch radius method. It basically comes down to one thing, and that is the pitch measurement dimension is not orthogonal to the radial dimension. So it's not necessarily an independent coordinate. With ring core designs, the number of the number of cores that you have improves the pitch as an azimuthal coordinate. 2 core turns out to be very bad, in fact, the worst possible, and things improve with 3 and 4 and more cores. The pitch gets more relevant. The constraint boundaries are not symmetric around the design core center, and we'll see some examples of this. And again, you could have a complicated design with many different cores, different pitches and whatnot, and so there's a lot of different things to keep track of. So here's an example. We're looking at a 2-core fiber with 50 micron pitch and half micron tolerances. We'll think of applying the pitch radius method to this. This is something that has been deployed in submarine networks, so it's an interesting fiber. The pitch was probably not exactly 50, but the idea is the same. So you're going to have 1 core on either side of the cladding center. It's going to turn out to be a very bad case for using pitch as a tolerance. The reason is because the pitch essentially is in the radial direction in this case. We'll see a picture in a minute. And if the distance between the cores is large, it makes things worse. And so here's another strange thing about using the pitch radius method is that the pitch, because it depends on 2 cores, now neither of them might be in the right position. And so you're convolving errors on different cores with each other. So it tends to make deciphering the problems a little bit harder. Even simulating the problems gets kind of hard. And then so we'll assume here that the core number 2 is going to be fixed in position. We're not going to concern ourselves with errors in core number 2, and we'll look at what happens to core number 1. So here's our 2-core fiber. cores symmetrically disposed about the cladding center. We're going to put a radial tolerance of plus or minus a half a micron on this, shown by these dashed blue circles. And then the pitch tolerance is going to be applied on core number 2, which we're assuming is at its nominal position. So plus or minus 0.5 microns on that. Again, not to scale, but this would be 50 microns plus or minus 0.5. And we find that the allowable positions for core 1 are going to be between the dashed blue circles and the dashed red circles. And so that's a funny shaped area that shows very weak constraint in the azimuthal direction. The radial direction is highly constrained, but the azimuthal is not. So that's a problem. If we look at it more to scale, it looks like this. Azimuthally, we have a very weak constraint. And if we look at what that constraint actually is as a function of this angle phi as we go around the designed core, the design position for the core, we find that in the x direction, we have the radial constraint acting. So it's giving us a 0.5 micron tolerance. So that's actually quite good. So for phi equals 0, we have a very good constraint. But as phi gets up more towards 90 degrees, our constraint sort of gets out of control, and we hit this weird peak, and it's going to happen again down here at 270 degrees. And so we get this awkward thing that our constraint is a function of the direction that the error actually is. And so it's actually not very good. And these errors are huge. I mean, we're talking 10 plus micron errors, so it's enormous, than far beyond what we would have expected by saying 0.5 microns is our tolerance. In the 4-core case, things are a little better. Here we're going to imagine that all cores except core number 1 are fixed. So we say core 2 and 4 are fixed. Their pitch limits are shown by the red. This is for core 4, and the orange here is for core 2. We're focusing on core number 1 right here, and its radial constraints are set by plus or minus 0.5 microns here in the blue. So again, we have to be inside all these colored boundaries, and so that says that the extent of control is in the violet area again. It's looking more circular, and by the way, the dashed black circle here is what we get from the rotate to template method. So you can see we're approaching that, but again, we still have some non-uniformities around as we go around the design core, and they're not as bad as they were in the 2-core case, but still, a square root of 2 higher in certain directions than in others. Okay, so briefly we'll look at a little bit of vector math here just to see where this azimuthal dependence of the pitch is coming from. And there's a couple details in the paper that you could read about if we don't cover it well enough here. But anyway, the bottom line is, if we look at just 2 cores on the end face of the fiber, we'll locate one along the x-axis of a coordinate system which we set up. And our second core will be out here somewhere. We'll just say it's here. That's the design position in green. The actual core might be in red over here. It's not quite the right place. Has some radial error and azimuthal error. R and S are distances. If we locate these cores by these position vectors, R1 and R2, we can actually talk about a pitch vector, which is just the sum of these 2 position vectors. And the pitch vector looks like this. The size of the pitch vector is its magnitude. We dot it with itself, take the square root, and we can work out the magnitude of the pitch vector, and then we can figure out how that depends on these angular offsets. So we just take the derivative of the magnitude of the pitch vector with respect to this guy, which is he's just R2 times d phi 2. It's a differential length in the phi 2 direction. We take the derivative, we get this crazy expression here, which says some things that are obvious. One is that if phi 2 becomes 180 degrees, in other words, this core was over here where it was for the 2-core fiber we talked about earlier, the numerator goes to 0, and actually our pitch magnitude will have no angular dependence in it. So to first order, it's free of angular dependence at all. So it's going to be very insensitive to errors in angular movement. The other interesting point is when phi 2 is equal to 0, it looks like the same thing might happen there, because the numerator goes to 0, but it turns out the denominator also goes to 0. So it turns out that phi equals 0, you get the very best angular information from your pitch, because in that case, the core number 2 is over here somewhere, and you can see that the pitch vector will be really in the azimuthal direction. So that's very helpful in that case. To summarize this equation, I just put together a couple of examples. One is if we choose the radius of the radial position of the two cores to be on a circle of 25 microns, we have the red tells you how the pitch varies with the angular position between the two cores, and it goes from terrible, i.e. no pitch utility for specification, to when the cores are on opposite sides of the cladding center to perfect. And so if the cores are right next to each other, as we just said, the pitch vector is totally azimuthal, and so we have good azimuthal control. In the case where the cores are not on the same circle, we could imagine having concentric rings with cores on each one of these rings. In this case, we move core 2 inward a little bit. The curve looks somewhat similar out here at large angles, but it has a maximum here, and it goes to 0 again when the cores are both on the x-axis. And if you look back at that picture, this would be the case where core number 2 is right in here. So if core number 1, 2, and the cladding center, if they're all collinear, you get no angular information out of your pitch at all, and so we'll get terrible control here in that case as well. Okay, so one thing we did was some Monte Carlo simulations. We want to be able to simulate what kind of connection losses we get. We'll actually work on fusion splice losses, because we can easily do these in the lab and do some comparisons. But to set up the Monte Carlo, we have to select some fibers that are satisfying the two criteria, either the pitch radius or the rotate to template criterion. And so what we did was we picked fibers that would uniformly fill the violet regions that were shown earlier. If you go back, like, we're going to uniformly populate this violet area with a bunch of cores which pass this particular pitch radius spec. And so by doing that, we're going to basically assume our manufacturing process is entirely out of control. We're going to depend entirely on these tolerance limits to essentially measure quality into our product, something, as you know, is in industry is a cardinal sin, but nonetheless, it's very educational in terms of comparing these constraints. So when we look at the pitch radius method, we see constraints look something like this. I've compressed the y-axis by a factor of 10 relative to the x. So it's a funny, instead of being circles, these red and green things are strange shapes. But anywhere where all the blue dots are, these are places that these are viable and passing core geometries in the pitch radius method. And this is, in this case, this is region of constraint on core 2. Here's its nominal, and core 1 is being fixed. So if we compare the rotate to template method in the same scenario, we have a nice little circle of radius 0.5 microns, which is our limit. And it's not dependent at all on the position of core number 1. Note, this thing actually is. I did this for the core number 1 nominal position, but core number 1 can actually wander back and forth in radius a bit because of our radial tolerance. So this is not the whole story. But nonetheless, you can clearly see the constraint on core number 2 is very weak in the azimuthal direction. So this thing shows a little animation of that previous case where core number 1 now is wobbling back and forth through its radial limits. So when it's at narrow radius, we get one set of core number 2 limits, and when it was farthest away from the cladding center, we get a different set of limits on core number 2. So it's kind of a complicated thing to simulate. But nonetheless, we did. With Monte Carlo, we just took a whole bunch of cores and basically figured out which ones satisfied the tolerance, a given tolerance, and then we used these to simulate to say, okay, we stick a couple of these fibers together, what kind of core offsets will we get? How well will the cores be aligned? And you can see in this case with the 2-core fiber, that the distribution of core offsets, and this is after we optimally align the two fibers, and we're still getting big offsets, is shown by this distribution function in red with a mean of 2.8 microns and a tail that goes on forever. In the rotate to template method, the distribution function is shown in red here. The maximum is around 1 micron, which is as you'd expect. It's if each core is off in the wrong direction by 0.5 microns, the net error would be something like a micron, and the mean is at 0.4 microns, so that's not too bad. If we actually look at using a splice model, a simple splice model, which says that the splice loss is proportional to the square of the core offsets, we get numbers like this in red for the pitch radius method. So a lot of very large splice losses, and the 97th percentile point for these losses is at 8.4 dB, way out here. In the case of the rotate to template method, we get the green data, and 90%, the 97% point is at 0.1 dB, probably an acceptable number. So you can see an extreme difference for the two-core case, which is the worst for the pitch radius approach. So we did the same thing with 4 cores. In this case, the core offsets after best alignment are much closer for the two conventions, maybe 25% difference in the means. The tails are still a little bit big when we look at the splice losses on the pitch radius approach, but things are much closer. And if we go to 8 cores, for example, probably the pitch radius would be great. Okay, one last thing that I wanted to add here is we did some measurements to verify some of our work on prediction of losses given core offsets. And what we did was we took 5 separate fibers with a range of core geometries, some good, some bad, and we randomly mixed them together, did 10 splice repetitions of each case, and plotted them out here, and we showed the loss on each of the 4 cores for each of our fiber combinations. And the predicted loss can be obtained fairly simply from our splice model and knowing the core geometry, so we measure these things beforehand. And we generally find that the predicted loss in the yellow points here more or less tracks the mean that we see when we do our splice testing. There are some mysteries here. For example, why we get so much variation when we actually measure things experimentally. Not all this is fully explained at this point. We see certain cases where actually the variation is very small. But nonetheless, the idea of the rotate to template approach seems to work pretty well. This is the algorithm we use in our splicer, so we are trying to get the best, in a least square sense, alignment between the cores of the two fiber. Instead of aligning to a template in this case, we're aligning one fiber to the other in our splice match. You can also see there's a very large range of splice losses. So, for example, this combination includes at least one of these fibers has a very bad geometry. So we're seeing splice losses up near a dB. In this case, these are 2 fibers with very good geometry, and so our splice losses are below 0.05 generally. And this is what we see typically when we're doing low strength splicing on 4 core fibers, and then other ones in between. Okay, so I realize I've shot through this thing probably faster than I intended. However, we'll have more time for questions. But so the core identification part of the talk, I just overviewed a couple of the common ways that people have considered using identifying cores in the fiber. It's generally believed that you are going to need to do something along these lines, and so markers is a popular approach. It's unpopular from the sense that it adds cost to the fiber, potentially could add impairments if not done carefully and verified. For example, the marker gets too close to core number 1. What does that do to the loss of core number 1? Or does that affect some of the glass properties of core number 1? So, for example, it has a more of an elliptical shape, and we start getting polarization mode dispersion problems, things like that. So if you could do without a marker, it'd be great. Marker does add this business of polarity. at least when you have more than two cores. And so polarity tends to be a problem that just drags with you everywhere from fiber manufacture to cabling to installation. And those kind of problems, if you can avoid, would be good to avoid. So core identification looks like it's probably going to be a marker is probably the way we're thinking about it. Though with the exception of submarine, because the submarine market has shown some interest in a two-core fiber. There have been some fibers sold in that market that have offset cores and don't have markers. And so in that case, maybe offsetting the cores is fine. But the bulk of the talk has been talking about pitch being such a weak constraint on tolerancing the dimensions. Now, it's not to say that pitch can't be used. It can be. It can add an extra criteria. For example, if you use a rotate to template method, which I'm advocating here, and we've applied successfully in fusion splicers and whatnot, you could use a rotate to template method and then add a pitch requirement on top of that. So, for example, you wouldn't allow adjacent cores, to be extremely close or extremely far, as the rotate to template method would allow them to be. You could restrict those extremes a bit by saying the pitch has to be more tightly controlled. So pitch still has a role. It also has a role in classifying fibers for sure, because when people talk about a multi-core fiber, one of the first things they're asking, okay, how many cores? What's the pitch? That kind of thing. That's what they want to know. There's very active work in ITU and IEC standards bodies right now on multi-core. They are working on identifying the optical properties of the cores, the geometry, as has been discussed here, how will we control the geometries, and in the IC case, how will those be measured? And there's still quite a few unknown things at this point. These bodies are working really only with 2 and 4 core fibers at this point. So they started kind of with the simplest designs and the ones they think are most likely to be market relevant. So I guess that's the end of my talk. If there are any questions, I'd be happy to entertain. Thank you.
Alan, thank you very much for this great, very in-depth work that you and your colleagues have put together. We do have a number of really good comments and questions that refer to certain slides. So if perhaps maybe you can jump back to some of these. The first one here on slide 5, it was noted that the fiber optics generally refuses to follow standard conventions. And even within the fiber, it's sometimes a radius and sometimes a diameter. Do you see any chance that we could find some harmonization with established standards like ASME Y14.5 or some of the others? Okay,
here's slide 5. Is that what we're talking about, or maybe I'm not sure what's...
I think so. I think again, it's you mentioned that standards are currently being evaluated and trying to harmonize different approaches. So the question was, do you see a chance that we might find a way to harmonize?
Oh, absolutely. Yes. And that's why IEC and ITU are working hand in hand. It's a lot of the same people actually in the two groups. So at least as far as that goes, and there's a connectivity group in IEC as well that's tied tightly into this. So yeah, there are a couple other groups. APC is one of them, and IEEE potentially has some input, though not on the details of core geometries. I don't think there are any, so I set this presentation up as a sort of a conflict between the pitch radius and the rotate to template methods. It's not really a conflict. I think both of these things will have their place. They will probably be, as I was saying at the end, they will probably both be used to some degree. I think the rotate to template is going to be very key because the hard work of getting the alignment close is going to be done, I think, with that method. If you add pitch onto that, you may further refine that and discard some of the rotate to template fibers that would have some cores that are either too close together or too far apart. That could certainly happen and would be sensible. But But yeah, I don't think the methods I'm talking about are necessarily in conflict. It's just that I think I was trying to make the point that we want something that looks like this in multicore. This is a beautiful single core thing, very controlled, very understandable. But we like something similar to this in multicore, and the rotate to template method, with all its awkward features of having a template involved, I think gives us that.
Right. On slide 8, how did you determine the origin?
Yeah, in this case, we can do these things arbitrarily. So for example, your template could be set up with a bunch of these, dashed cores all over the place, and let somebody called this one core number 1, let's say. We could arbitrarily create, without loss of generality, we could put a coordinate system on that. If we want to put core number 1 on the x-axis, we can do that. We're not losing anything by doing this, because our measured fiber has to be measured against that same coordinate system. And when we have test sets, there already are test sets that will do geometry measurements on multi-core, and they set up their own coordinate system, and it's just based on whatever the orientation of the fiber was that you shoved in there. It'll take the horizontal, of the camera, and project your multi-core fiber in that coordinate system, the horizontal and vertical of the camera. So it'll assign coordinates to that. So this result does not depend on the coordinate system. This thing that we finally come up with, we introduced the coordinate system for convenience when we do the rotations and whatnot. But at the end, this distance is coordinate system independent.
Good. Skipping over to slide 16, comment was made that the pitch radius are prone to uncertainty and not really functional. Do you have any thoughts on that uncertainty?
Yeah, I mean, we're showing the uncertainty right here on slide 15. The concern is you don't get very tight constraints in the azimuthal direction for certain core patterns. And for the case of the 2-core pattern, where it's symmetrically disposed around the cladding center, we see just almost no control in the azimuthal direction. So the cores can be way off. If we have a picture of this, yeah. So core number 1 can be way out. This, core number 1 out here where the pointer is, that would be passing by the pitch radius tolerance that allows 0.5 microns on each of the pitch and the radius. So, and this would create a tremendous connection loss. So you don't want to do this. So pitch radius by itself is not good. Pitch in concert with some other things like the rotate to template would be great.
Good. Why not simply use radius and an angle defined by fiber 1? This would be a typical coordinate system without orthogonality issues. This is harder to measure manually, but should be more straightforward with a digital imaging system.
Yeah, but I think your fiber 1 a perfect fiber, or what? If your fiber 1's a perfect fiber, I would call it a template, and that's exactly what we're doing. We're going to put this template into our whatever it would be, our fusion splicer or our measuring instrument, and we'll project the image against that. If we're going to do connectivity, we might also want to do the same thing, and then literally rotate our fiber in that connector until things align within the allowed tolerances. If I understood your question right.
Okay. How did you compute the splicing losses from the core eccentricity?
Yeah, we have done some measurements of intentional offsets of cores. They're actually well known. It's actually very much like single core offsets. So the models look almost identical, and so we used, given the specific type of fiber we had made, we have a lot of empirical data on what the loss looks like as we offset the cores, and so that's what we used when we did these simulations.
And this question, do you have the rotate to template method published elsewhere? Is that in another document?
Yeah, it is in certain forms and fashions. There's been a fair amount of work on this, the multi-core fibers fusion splicing, and there's been some details of how the algorithms work that figure out how much you should rotate the fibers, and they are in some sense based on a least squares fitting of minimization of the distances between the cores that need to be aligned. And so that stuff's been published extensively. I think in standards, we're going, there are a couple of technical reports. Well, there's one technical report being worked on in IEC right now. One has already been published in ITU. These are special technical reports on MCF. The one in IEC does have some detail on the kinds of equations I was just showing. And I think in one of the ITU measurement documents, we're going to also have some detail on how to do this rotate to template optimization. One giant outstanding issue is the business of radial offset. In addition to angular rotation, how about radial offset? And it's possible that may go in there as well. But I think someone needs to figure out, is there a simple analytical answer for that problem or not? Don't know.
Can you disclose which machine you used to make the lab experiments?
Yeah, I'm happy to do so because I'm advertising my own company, but I didn't think you wanted me to do that. So I didn't put it in at this point, but I will. Yeah. Yeah, the Fitel S185. Actually, we use the PM ROF version. So it's a polarization maintaining kind of splicer, and it has a ring of fire structure to the electrodes. There's actually 3 electrodes in a set of 2. So we think that gives us a little better kind of uniformity around the edge of the fiber, so that if we have 4 cores like this, we don't just get a big arc just shooting through the center, but we get all of the cores sort of uniformly heated. That's the thought. But there are a couple out on the market, at least one other big competitor that offers something I think does a good job as well.
Yeah. And just a few general comments here. Becky may have stated it, but in a minute, I'll be providing you with Alan's email address if you want to reach out to him directly and get a few more details or answers to your questions. And also this webinar and the paper can be found through our IWCS.org website. So you can review it again later or share it with your colleagues as you wish. Just time for another question or two, and then we'll wrap up. Regarding the fusion splicing, any thoughts on feasibility and capability to splice MCF ribbons or complete multiple MCF splices at the same time?
Yeah, that's a difficult problem, and we do have people working on such a thing, but as you can imagine, you're going to try to individually rotate fibers to match another set of fibers. That's pretty hard. And another difficult problem is making multiple fiber connectors, multiple fiber multi-core connectors. So adding more multi-core fibers into a multiple fiber connector, MPO or something, that also is highly desirable and probably required for data center use, but at this point, very challenging. So connectivity has always been a bit of a challenge, but now it's gotten a lot more challenging.
One last question. Can you tell share the fiber length of the multi-core fibers that you tested in the lab?
The length, usually quite short. When we do splice loss testing, usually 20 meters or even less, 10 meters, we make sure we don't get higher mode propagation. So we do some mode conditioning. But yeah, for the most part, a few tens of meters is enough. So we're using power meter. We're using power meter and lasers. We're not using OTDRs, so we don't need long fiber lengths.
Right. I want to thank the audience for sharing a lot of excellent comments and perspectives in the chat. You might want to capture that and go back and review some of those comments. They were excellent. So I want to thank everyone for their participation and the excellent questions. Obviously, it's an interesting subject, and the impacts on codes and standards and review in the future is certainly very relevant. So I want to thank Alan and the entire Lightera team who contributed to this. Roman Shabakin, who presented this last October. And we look forward to hearing more information going forward at upcoming IWCS events as well. Again, as I mentioned, here is Alan's email address for you to reach out to him directly for any further questions or commentary. And again, we have these webinars archived on our YouTube channel, but you can access all of them that date back over 10 years now. It's amazing. We've been putting these on for almost 10 years. So there's a lot of really good content that you can view and be accessed from our IWCS.org website, along with the technical papers. So again, these events occur a couple times a month. The technical paper webinars are typically the third Friday of each month at 10:30 a.m. Eastern USA time. The next event will take place on Friday, July 17th. And it will be another excellent paper that got high accolades at the Pittsburgh conference. And look forward to having you with us. And please feel free to share our announcements with your colleagues so that they can also join in and register as well. Before we conclude, it's important that we recognize and thank our partner level sponsors at IWCS who contribute greatly not only to the content, but also their generosity to help us bring these events to you and these technical innovations and information to our global audience. So again, thank you to these leading suppliers in our industry for their support. And all of us are very excited. We're working hard to pull together an excellent conference coming up. It's our 75th anniversary for IWCS, and the forum will be the first week in November in Orlando, Florida at the excellent venue, the Gaylord Palms. And we'll have a fun celebration on the Monday evening with some fantastic entertainment. So we hope that you'll make plans to attend. The preliminary program should be coming out here shortly. We've got excellent content that we've reviewed over the last month or so. And again, we hope that you'll make plans to join us. And please stay tuned, not only to your inbox, but also from our website and social media to learn more as the information comes together. So I want to thank you for joining us today from wherever you are. Again, good morning, good afternoon, good evening. Some of you I see are late into the evening, so hopefully you've had a glass of wine or a beer to join with us today. So thank you and have a great weekend.
Thanks, Dave.
Thanks, Alan.